In the second video, what we're going to do is we're going to apply the one-to-one property of the exponential function to solve equations as well. This time we're going to apply it to solve logarithmic equations. So you get a brief description here, another statement that follows the one-to-one property of exponential functions. If x equals y, now x and y are the exponents, so if we know the exponents are equal, as it's saying here, then if we take b to the x and b to the y, they have to be equal. So what we're saying is that we know the exponents are equal, then if we raise it to the same base, if the b's are the same, the bases are the same, then b to the x has to be equal to b to the y. We can use that idea to solve logarithmic equations such as this one. Now when I look at this statement, what it tells me is I have an exponent. Remember, logarithms equal exponents. So these are both exponents. This is an exponent that's equal to another exponent. So the exponent log base 2 of x is the same as 3. Well, if the exponents are the same, then if we raise them to the same base, and the base that they choose is log of an exponent base 2. That's a good selection since it's a log of base 2. We would take 2. If we raise 2 to the log base 2 of x, it has to be equal to 2 raised to the third. Okay, so here's the concept. One-to-one property says if we know the exponents are equal, that's what this statement is saying, then if we raise the same base to those exponents, they have to be equal. So we're going to choose to raise it to a base 2 since it's a logarithm base 2. The reason that we want to use a log base or a base 2 is because it's a logarithm base 2, and you got to remember your inverse properties of logarithms. If it's 2 raised to the log of base 2, they're inverses and they cancel, so x is nothing more than 2 cubed. Now this is not the only way of thinking of this. This is one way. This is the one-to-one property of exponents application. There's a couple other strategies that are just as good and I think probably even easier. Another way of thinking about it is log of base 2 of x equals 3, and that is we can convert this thing immediately, just convert it into an exponential statement. It says 2 raised to the exponent of 3 has to equal x, so obviously x is equal to 8 as well. And the third way, and this is kind of what will end up being the mainstay, I think, is if we get a log equation. The reason that we studied logs is because logs are the inverses of exponents. So if we want to undo a log base 2, we exponentiate both sides to a base 2. Now what I'm going to do is I'm going to take this, I'm going to exponentiate it to a base 2, and this to a base 2. And really what we're doing is we're thinking of it in terms of this one-to-one function. If I want to get rid of a log of base 2, what would be the inverse of a log base 2? And that is to exponentiate to a power of base 2. As long as you do it to both sides, you create an equivalent expression. So this is what they're saying here. It is called exponentiating each side of the equation. Now what we use to exponentiate is always going to be what the base of that logarithm is. And now we're back to the same concept that the log of base 2 and exponential base 2 cancel, and your solution is whatever 2 to the third is. So that's a little preview of what we're doing. We're going to come down, we're going to apply the one-to-one property and some of those other concepts here on 3 examples. So first thing, when I look at log statements, what I want to do is first of all, I want to try to isolate the logarithm. So isolate the log statement, or in this case, it could be a natural log, so whatever it is, isolate the log. Then the second thing I want to do is I want to use either the one-to-one property, just do it like this, which really is exponentiating both sides to the same power, and then what we'll do is we'll solve the resulting linear equation. Or I guess it doesn't have to be linear, solve the resulting equation. It could be linear. We will also see some quadratics that are going to pop up in here as well. So okay, let me see how we can kind of apply this to the problems at hand. So the first thing I want to do is I want to isolate the natural log. I want to isolate the logarithm. So to do that, I'm going to multiply both sides by -3. So that means the natural log of x, I misspoke there, I want to divide both sides by -3. So -24 divided by -3 is a +8. Now I've isolated the log. Next thing I want to do is I want to use this one-to-one idea. If the exponents are equal to each other, then if we would exponentiate them to the same base, e, I'm choosing e because it's a natural log is a base e, then that would say that e raised to the natural log of x would have to equal e to the 8. But as we've learned in the lesson 3.2, if we have an exponential, a base e, followed by a natural log, raise to the natural log of base e, these are inverses, so those are your inverse ideas, and x is simply whatever e to the 8 is. Now you can take your calculator and you get an approximation for that if you want to, whatever that value is, and again, it's nothing more than just grabbing your calculator, getting it started, and saying, all right, let's clear this so we have a clear screen. We'll go second, we'll go e to the x, we want to raise e to the 8th power, and that means our answer is approximately 2,980.96. 2980.96, I think is what I had on the board there. So it's not that big a deal for me if you round it. To me, I'd rather see this result here. Okay, so that's one example I demonstrated. Isolate your log, use your one-to-one property. If you like that idea, if you don't like that idea of exponentiating, here's what I'm going to come back to one more time. If it's a natural log of x equals 8, here's your choices. You can use this one-to-one property as I showed you here. Another way is if you get simple log properties like your log equations like you have here. Remember, you can always change these into exponential, so I can go ahead and just change it to an exponential. Since this is a natural log, it's a base e, so it's got to be an exponential of base e. Logs always equal exponents, so e to the 8 has to give me the antilog x. There's another simple way of solving that equation. And like I said, probably by the time we get done doing these, as they get more and more complicated, what we'll end up doing more times than not is we'll say, well, what would be the inverse? And this kind of goes along with the same stream of thinking that we have with all the other equations. What do we do to get rid of something that we don't want? Well, if it's a natural log, we have to exponentiate both sides to a base e. To exponentiate to base e, we'll undo, or it's the inverse of a natural log, so they cancel, and x equals e to the 8th. So, like I said, we've got a variety of ways that we can approach these. I think in the end, we're probably going to like the idea of you doing the inverse, because that's how we do all these others. Okay, so, 2b, first thing I want to do is I want to isolate this logarithm with its argument. So to undo this, we're going to think about using our PEMDAS backwards. Since they're getting more and more complicated, we want to get rid of any addition subtraction first. So I want to get rid of adding 4. The inverse of adding 4 is to subtract 4, so it's 16 minus 4, which is 12. After we get done doing that, we want to do the inverse of, now we're at the multiplication division stage, we want to get rid of multiplying by 3, so we will divide by a negative 3. So the log of 5x, common log of 5x equals 12 divided by negative 3 is a negative 4. And at this stage, what I'm going to do is I'm going to go fall back to this inverse. What would be the inverse of a log base 10? Well, the inverse of a log base 10 is to exponentiate both sides to a power of 10. 10 raised to log base 10, those are inverses. So we have 5x equals whatever 10 to the negative 4 is. Well, 10 to the negative 4 to me means 1 over 10,000. And you can also write that as a decimal, 0.0001. Next thing I want to do is I want to solve this for x. So to get rid of multiplying by 5, I do the inverse, and that is to divide by 5, or in this case, since there's a fraction, I'm going to multiply both sides by 1/5. So what our answer would be is 1 over 50,000. And you can also get a decimal approximation for that, or a decimal answer for that. It's not an approximation. I believe if you take 1 divided by 50,000, it is 0.00002. And you can double check on that, but I believe that's right. Okay, so there's another modeling of how to solve these log equations. Third equation. We already have the log isolated. Now this being in parentheses, since this is in parentheses, I cannot separate it from the log of base 3. This thing that I put in parentheses, this is what they call the argument. It's called an inviolable, yeah, I can say that most of the time, but not today. You cannot violate that argument. It's basically the base word is violate. If you violate it, that means you tear it apart without getting rid of the logarithm first, so it's inviolable. So you got to get rid of the log base 3 first. So our log is already isolated. Our argument is all contained inside those parentheses. So how do we undo a log base 3? To me, the easiest thing to think about is the inverse of log base 3 is to exponentiate to base 3. And this is really what they're calling their one-to-one property. A 3 raised to log base 3 are inverses, so we've got x squared minus 1 equals 3 to the 4th. So 3 to the 4th is 81. Now I have to undo subtracting 1, so that means x squared equals 82. and then x has to equal, we got to take the square root, so you got to be careful whenever you square root. You got plus and minus, because this value got squared. We wouldn't know if it was a positive or negative. The square root of 82. And this in itself is a great answer. What you might want to do is come back in here, find out what the approximate answer is. So we will do here we go. We'll do the second. We'll do the square root of 82. And we can round that off to a few decimal places. How about 9.06? So x is approximately a positive or negative 9.06. Okay. So using the one-to-one property to solve logarithmic equations, we're also looking at calling that exponentiating both sides, or we can also just use our idea of we can change log functions into exponential functions. So there's some leeway here, there's some flexibility, but as I said, I think in the long run, we'll end up trying to think of it as inverse operations.